Okay, and good morning. Still morning, and we shall continue with our next topic, which is microfabrication photolithography. The process, which is kind of the heart of the process for microfabrication. So that determines the capability to make it small, the process that being able to make sure that we can produce a small size of the structure as well as the intended shape and structure as well. So photolithography is a common process for the semiconductor fabrication and also used in MEMS fabrication. So the extension of the semiconductor being used in MEMS to make the microstructure in 3D also part of the process is photolithography. So what is photolithography? We look into the definition of photolithography and then we look into the details of photolithography. So photolithography is a microfabrication process that uses light to transfer a pattern from a mask onto a substrate, typically a silicon wafer, using a light-sensitive material called photoresist. After the photoresist is applied, exposed to the light through a mask, and developed to reveal the pattern, the substrate can be modified through processes like etching, forming the intricate layers of the integrated circuits and micro devices. So you see that a few keywords here has been introduced before. One is photoresist, which is a crucial material for photolithography process. As the names appears here, a material which react to photo or light. And then we have a mask. Then we have a process of etching and forming, etc. So this etching and forming will be introduced later, but in this process, we will be focusing on photolithography process. So the word itself, photolithography, is from a Latin word. Photo is light, as everybody knows, and litho is stone, and graphy is writing. So the actual meaning is photolithography, light, stone, and writing. And patterns are first transferred to an imageable photoresist layer. So this is the process of photolithography. Then photolithography is the binary pattern transfer. There is no grayscale, color, nor depth to the image. So the image is just about the image transfer is on the pattern that been transferred without. When you remove the part of the resist that you can have the image, the actual image you can see. But before that is just a process to transfer the pattern in a binary way, which is mentioned here. And photolithography is an optical means for transferring pattern onto a substrate. It is essentially the same process that is used lithographic printing. So photoresist, as mentioned before, is a liquid film that can be spread out onto a substrate, exposed with a desired pattern, and developed into a selectively placed layer for the subsequent processing. So it's a polymer material which is sensitive to light. So in a glance, this is how the process of photolithography, just a quick understanding of this. For example, we have a silicon substrate. Normally in the process of microfabrication or IC design, it will have silicon dioxide on top of this silicon substrate. Then we coat photoresist on top of this substrate. So once you have this substrate, normally we will go through curing or baking. Then it depends on the use of photoresist. I will introduce the types of photoresist. In general, we have two types, which is one is positive photoresist, one is negative. You can see that with the same mask, this is the mask here. Then you expose to UV. Then if it's negative, this will be remain. The pattern where it's exposed to the light will be hardened and remain on the substrate. Whereas in the positive photoresist, the exposed will be removed. So you are hardened, I mean, because it's react and it will cut the polymer chain, then you can remove the material. The exposed to the light will be removed in the positive photoresist. So you get different pattern. So here you get the pattern where you expose to the light. For the negative and the positive, you get the pattern which is not exposed to the light, or you remove the pattern which is exposed to the light. So that is the difference. But we will see in details later. And then you do the process. This is kind of the overall process of photolithography at a glance. So a little bit of history for photolithography. So in 1826, Joseph Nicephore-Niépce in Chalon, France, takes the first photograph using bitumen of Judea and on a pewter plate developed using oil of lavender and mineral spirit. So this is the first use of this kind of masking. And William Henry Fox Talbot in England developed dichromated gelatin patented in Britain in 1843. And then in 1935, Louis Mings of Eastman Kodak developed the first synthetic photopolymer, polyvinyl cinnamate, the basis of the first negative photoresist. So that was in 1935. Then in 1940, Otto Suess of Karl Div of Hoch, Germany, developed the first diazonicon-based photoresist, positive photoresist. So this is negative photoresist, this is positive photoresist in 1940. Then in 1954, Louis Plumbeck Jr. of DuPont developed the dichropolymeric letterpress plate. So this is kind of the beginning of the photoresist. So in the process of photolithography, you have to go through a certain process sequence. Basically, the sequence has to be followed accordingly in order to obtain a good transfer of pattern onto a substrate. So here you have surface preparation. Surface preparation is crucial in order to have the polymer to be attached to the material in a good manner. So if the surface is contaminated, it will be, you might have the problem in terms of the pattern transfer to the surface because the addition of the photoresist is not good. For example, because of due to some contamination, it is the addition is too strong, for example, then it won't be good. The surface preparation referring to the substrate surface, and you do the cleaning. For example, we will look into the process of RCA cleaning, etc. for the silicon surface, silicon wafer. So then we do spin coating onto the polymer, the photoresist spin coating on the wafer substrate in order to have a thin film on the substrate. Then because this is liquid form, and then you pre-bake softly to make sure that some solvent is evaporated so that you can have a quite stable photoresist on top of the surface. Then you do alignment to the mask so that you will transfer the mask accordingly, nicely on the substrate. Then exposure, meaning to expose the mask and the photoresist to the light, UV. Then you do development to get the pattern. Then you do post-bake, meaning to harden the polymer further, and processing using the photoresist as the masking film. So meaning to say, if you have your structure, then that photoresist will be your mask. So first you transfer the pattern using a mask on a glass substrate. Then now your photoresist act as a mask for the structure that you're going to develop on your substrate. So that is, processing. Then the stripping, removing of the photomask or the photoresist, then post-processing, cleaning and etching, etc. So then this process might be repeated a few times in order for you to get certain shape or certain structure, depend on the complexity of the design that you have. Sometimes it's just about 1 or 2 times, but for the complex structure, you might need a few more times in order for you to obtain certain design. So the steps, as here is roughly mentioned, but now we go into the detail of the process, where firstly normally we use a wafer, a silicon wafer. Then we do the cleaning. The substrate is thoroughly cleaned to remove impurities. So impurities can be kind of oil, it can be some dust, etc. So this we have a special process later on where we introduce. Then barrier layer formation, a layer such as silicon dioxide is often deposited to serve as barrier. So here we will go through the process of, previously we have, I have explained on the process of growing silicon dioxide using process of dry oxidation and also wet oxidation, where you use steam and oxygen gas in order for you to have that silicon dioxide grow on the silicon surface. So the barrier, meaning if you want to have an electrical circuit on your device, then you have to have a barrier, because silicon is a semiconductor. Then you have a silicon dioxide to be your materials for insulator, electrical insulator materials. So that is silicon dioxide. And then a photoresist application. A thin uniform layer of photoresist is applied to the wafer surface via spin coating. This is a very common use, which is spin coating, high-speed centrifugal spinning. Normally, you just spin the photoresist on the substrate, then you can get a uniform thickness of the photoresist. But of course, there are some kind of process optimization in order to get a good thickness of the photoresist on the spin coating process. Then the photoresist is heated to drive off solvent and improve its photoreactive properties. That is a pre-baked process. Then go through the mask alignment. Photo mask containing the desired pattern is aligned with the wafer. So alignment is important. So the first process might be not that critical. If it's on the substrate itself, then the first alignment is just to make sure it's maybe at the center of the photoresist, the wafer, etc. But the subsequent process normally need to have a careful alignment, because the process will determine the structural kind of production, what you want to produce. If you have a pattern, then you want to have another pattern, it must be aligned accordingly to make sure that this is at the right position. So the mask alignment will be very important. Then light exposure, ultraviolet light or other radiation expose the photoresist through the mask, altering its chemical structure in the exposed area. Of course, the light exposure will be varies, depend on the photoresist types. there are a few types of photoresist accordingly will be used. If you using certain process that require deep RE, you might need to use a photoresist which are more robust in terms of using high exposure to deep RE. For example, PDMA, for example. So if it's just a photo mask for you to quickly expose to chemical into making a electrical pattern, you might use lower viscosity photo mask or different types of photoresist, different photoresist which is might be OFPR, for example, in order to make a very thin photo mask. So the light exposure will be varies according to what types of photoresist that you are using. And post-exposure bake, a bake is performed after exposure to improve the image quality. And development, a developer solution is used to selectively dissolve either the exposed or unexposed portion of the photoresist, creating a pattern layer. So here it depends on your photoresist. If it's positive, you want to remove the exposed part. If it's a negative, you want to remove the unexposed part of the photoresist. So this is the development process of the pattern. Then etching, the underlying substrate is etched to transfer the pattern from a photoresist to the substrate. So basically, when you develop, you are exposing part of the silicon substrate to the pattern that you are going to make. So if here etching is to remove the part as intended by the pattern. So meaning the exposed part will be removed by the etching process. Then resist strip, the remaining photoresist is removed to reveal the pattern substrate. So you remove all the kind of photoresist that you use. It's kind of wash out everything. So we go into the details of photoresist. Photoresist is a light-sensitive polymer or organic mixture that is applied to a substrate during the photolithography process. When exposed to the specific type of light, it undergoes a chemical change that alters its solubility, allowing the creation of intricate patterns on the substrate. So that is, kind of definition in general of a photoresist. So what consists of photoresist? In the photoresist, the chemical materials. Conventional liquid photoresist typically consists of three main components. One is resin or the polymer itself. So a binder that provides the photoresist physical properties such as addition to the substrate and chemical resistance. It forms the backbone of the photoresist. So basically the main component is the polymer itself, the resin. Then you have a photoactive compound, the light-sensitive component. When activated by light, it modifies the solubility of the resin in the developer solution. So then you have solvent, keeps the photoresist in the liquid form so it can be applied to the substrate as a thin, uniform layer via spin coating. So solvent might have different percentage in the photoresist. If you want to have maybe high viscosity or low viscosity, it will be dependent on the use of the solvent itself. And we have talked about the types of photoresist before. In details, photoresist are primarily categorized into two types based on their reaction to light. One is called positive photoresist, which the portion of the resist exposed to light becomes soluble and are washed away by the developer solution. The unexposed area remain on the substrate. So that is what I've shown on the first at a glance of what mechanism it used. So this is positive photoresist. As a composition, a common type is a mixture of novolec resin and diazonophotiquinone, DNQ, sensitizer. Light exposure converts the hydrophobic DNQ into a hydrophilic carboxyl Salicylic acid, increasing the solubility of the resin in the aqueous-based developer. Basically, the exposed part will be, part of the remover part. The pattern creates a pattern that is the same as the mask design. So whatever you design the mask, that will be the pattern that you will transfer. Meaning to say the pattern, the black part of the pattern will be transferred because you are removing the exposed part. So advantage, known for its high resolution, making it suitable for manufacturing advanced semiconductor chips with very fine features. And the disadvantage, low sensitivity, requiring a high exposure dose. So the light intensity. And the second type is a negative photoresist, and the portion exposed to light become insoluble in the developer solution due to cross-linking. The unexposed area are then dissolved and removed. So it's the opposite of the positive photoresist. So you are removing the unexposed part. So composition, a traditional negative photoresist contain a polymer like cyclized polysulfide and a bisulfide sensitizer. Exposure to light generates radicals that cross-link the polymer chains. Modern negative resist often use a chemically amplified system. So it creates a reverse or negative image of the mask design. So if by design you are having the basically the unexposed part will be removed. So you are your pattern will be the exposed to the light. So it's the opposite of your design will be patented on the substrate. So generally more sensitive than positive resist, requiring a lower exposure dose. It also tends to have excellent addition to silicon. And the disadvantage has a lower resolution due to the swelling of the resist during the development process. So, okay, we have looked at this process before, but in detail, we have the photoresist. This is negative. You coat on the substrate. Then you have photomask. Photomask is basically a pattern on a glass that this is the pattern basically where the light cannot pass through, but the exposed is where the uncovered glass is where you have your light will pass through, then you will transfer the pattern to the photomask, to the photoresist. The transfer pattern on the photoresist for the negative is where the exposed to the light part will be remain. This is a negative photoresist, but in the positive photoresist is the exposed part will be removed. So you get whatever pattern that you write or you draw on your photomask will be transferred. But in this case, on the negative photoresist, you are the opposite. When you design something, you have to think that you are removing the exposed part, the unexposed part, which is you want to have the pattern of exposed part will be remain here. So that is where we have to be careful when we design for photoresist. We have to know that you will use the negative or positive photoresist in order to make sure that you transfer the right pattern or you remove the right parts of the design to the substrate or to the photoresist. So key properties of photoresist. The performance of photoresist in a manufacturing process is determined by several factors. One is resolution, the ability to produce the smallest possible feature size. So the resolution will be determined by types of photoresist. So sensitivity, the minimum light energy required to produce a well-defined features. And addition, the ability of the resist to stick to the substrate without lifting, especially during etching. So, the sensitivity, the resolution and sensitivity, we try to not to expose, when we do patterning, transfer the pattern to the substrate or to the photoresist, we try to do not to expose it for too long. The longer you expose will have the effect that your pattern won't be as intended, meaning to say it might go beyond the size that you have designed. Because of the longer you expose the light scattering might happen. So it might go beyond the size that you have designed. So that is, I mean, you want to have high sensitivity at certain extent. So it goes the same with the addition. If you have the ability for resist to stick to the substrate without lifting, then it will be good. But the stronger addition to this substrate also not that good, because it might be difficult for you to remove the materials later on. And contrast, the difference in dissolution rate between the exposed and unexposed areas. Higher contrast leads to sharper pattern edge. And edge resistant, the ability for the pattern to resist to withstand the harsh chemical or plasma etching process used to transfer the pattern to the substrate. So edge resistant is kind of, because we want to develop the pattern later on, meaning to say you want to expose the silicon. If you have, in the case of silicon substrate, you want to expose the silicon to chemical or to deep RE in order for you to develop the structure. So if the edge resistance is not good, then after a while, after just a few minutes, for example, you will have the photoresist to be removed. So you will not be able to make a pattern accordingly. But of course, there are a few types of photoresist that has been tested to do at certain extent with some chemical or some process that can be used accordingly. All right. Next is on the cleaning process of the wafer. So in preparation, the surface preparation of the wafer need to be done carefully in order to remove the contaminant on the substrate, on the wafer itself. So one of the process is, the commonly used process is called RCA cleaning. The RCA clean is a wet chemical process for removing organic, ionic contaminant from silicon wafers in semiconductor manufacturing. It was developed in 1965 by Werner Kern at the Radio Corporation of America. That's why it's called RCA. The process is essential for preparing wafers for high temperature processing steps like oxidation and diffusion. So the standard process consists of 3 main steps, each using the heated chemical solution with a thorough rinsing in deionized or DI water after each steps. So typical contaminants that must be removed prior to photoresist coating, normally dust from scribing or cleaving, minimized by laser, because in preparation for the wafer, you do slicing, you do dicing, etc., and the handling of the wafer might get contamination on the surface of the wafer. Then atmospheric dust minimized by good cleaning room practice. Normally, we know that we do MEMS process and semiconductor process in clean room, but still there might be some contamination as well. So abrasive particles from lapping or CMP, and the process of polishing the surface of the wafer also might previously remain some contamination. Lean from wipers and photoresist residue from previous photolithography, minimized by performing oxygen etching. So as I mentioned before, in order for you to get this design or a structure on your wafer for a certain design, you might go through a few steps of photolithography as well. So the few steps, the photoresist and the etching, everything might remain some contaminant. So this contaminant need to be cleaned up before you proceed with the next process. bacteria minimized by good DI water. In the clean room, we use deionized water basically in the process, the whole process. Film from other sources, solvent residue, H2O residue, water residue, and photoresist or developer residue, oil and silicon as well. So a standard process is to degrease whatever oil, for example, the grease on the surface. The process is 2 to 5 minutes soaked in acetone with ultrasonic agitation. So ultrasonic cleaning process, and 2 to 5 minutes soaked in methanol with ultrasonic agitation, and 2 to 5 minutes soaked in DI water with ultrasonic as well, and 30-second rinse under the free flowing of DI water, and spin rinse dry for wafers, and with a nitrogen blow off during for tools and chucks. So we normally use nitrogen in the clean room to blow the air or to clean the surface. For particularly troublesome grease, oil, or wax stains, start with a 2 to 5 minutes soak with TCA or TCE with ultrasonic agitation prior to acetone. So this is a more harsh process. So TCE is a kind of carcinogenic. It's less so acetone is flammable. Methanol is toxic by skin absorption. So this must be careful. So that's why in clean room we use mask and we use glove, etc. PPE. And the step number 3 for wafer cleaning. The third step is designed to remove metallic or ionic contaminants, and with a solution, a heated mixture of deionized water, hydrochloric acid, and hydrogen peroxide. And what happens is the solution, also known as a hydrochloric peroxide mixture or HPM, is heated to approximately 75 to 80 degrees Celsius. So this strong acid and oxidizing mixture effectively dissolve and remove any remaining trace metal or metal hydroxide. So the result will be the SC2 step, standard clean step, leave a fresh, thin, passivating oxide layer on the wafer surface, which protects it from further contamination. Then you have a final rinse and dry. After each step, wafers are rinsed with overflowing deionized water to remove the chemical solution. Then you dry with nitrogen gas to prevent water spot and recontamination. And sometimes we also dry it in oven. Okay, and sorry, I think I go pass through. I think it's okay. Pass through different steps. Okay, so the next is on the water priming. So adhesion promoters are used to assist resist coating, basically. So what happened is we want to make sure that resist is adhere to the surface properly. So resist adhesion factor, mostly about moisture content on surface and wetting characteristic of resist, type of primer, delay in exposure and pre-bake, and resist chemistry, surface smoothness, stress from coating process, and surface contamination. So ideally, we want no water on surface on the wafer surface, and wafer are given a sink step prior to priming and coating, 50 minutes to 80 to 90 degrees Celsius in the oven, in the convection oven, basically. And for silicon, primers form bonds with surface and produce a polar or electrostatic surface. So you want the surface to be polarized, and most are based upon siloxane linkages, which is SiO and Si. So with this, you have a few chemical, then the silicon is ready. Used for gallium, if the surface is on the gallium arsenide, has a polar surface, then you use monoxylene C and trichlorobenzene and xylene for the surface primer. So for the spin coating, wafer is held on a spinner chuck by vacuum, and resist is coated to uniform thickness by spin coating machine. So basically, a spin coating, I think I have a figure. Okay, this is a spin coating layout basically. So you have a chuck here, which is a vacuum chuck normally. So vacuum chuck will hold this wafer on top of this chuck. So you spin this whole thing in order to spin coat the resist. So typically with a 3,000 to 6,000 RPM for 15 to 30 seconds. So it depends on how thick you want the resist to be on the surface and what is the photoresist material. If it's a high viscosity and you want to have a thick film, then you reduce the spin RPM. If you want to have a lower thickness, which means thin films, you might want to have a higher spin RPM. So resist thickness is set by a primary resist viscosity and secondary spinner rotational speed. So this is what I have explained. Resist thickness is given by T equal Kp square divided by square root of W, where K is the spinner constant, typically 80 to 100, and P is resist solid content in percent, and W is the spinner rotational speed, RPM. So most resist thickness are 1 to 2 micrometer for commercial SI process. So this is, typical spin coating process, where normally we will go through a slow coating, slow RPM, then we increase the speed a little bit. Then this step has its own purpose. First is to spread the photoresist on the surface. Then this is just to stabilize a little bit. Then this level out is to remove whatever, if you have a high thickness at the edge, these high spins will remove the high developed photoresist height here to be level, to be the same uniform thickness. So this is kind of typical setup or process parameter that is used for the spin coating of photoresist on the substrate. Okay, and this is what we call as, as I mentioned before, when you develop when you spin photoresist on the substrate, this is what happened. And when you increase the rotation speed at this level, you might get thickness, but will develop high thicker at the edge. So with a little bit higher revolution. So then you have this kind of thickness developed. Then if you want to remove this, you have to have higher speed of thickness higher speed of RPM for the spin coating. So this is what happened. And if you don't kind of go into the stage accordingly, the thickness of the spin coated film might not be as intended. So the tradition 30 nanometer variation in resist thickness due to non-uniform drying of solvent during spin coating. That is what happened. And 80 to 100 micrometer periodicity radially out from center to wafer. And edge bit residual reach in resist at edge of wafer. So this is what I've shown before, and can be up to 20 to 30 times the nominal thickness of the resist. So it's look easy, but somehow the process parameter need to be optimized in order to have a good thickness of photoresist. That is, I mean, what can be done here. So then we go into pre-bake, used to evaporate the coating solvent and to densify the resist after spin coating. And typical thermal cycles 90 to 100 degrees Celsius for 20 minutes, for example, in a convection oven, and 75 to 85 degrees Celsius at a 45-second on a hot plate. So the hot plate and the oven might provide you different quality of photoresist coating. So this is a direct heat. So that's why it's a very short, 45 seconds, but some careful need to be, aware. Commercially, microwave heating or IR lamps are also used in a production line. And hot plating, the resist is usually faster, more controllable, and does not trap a solvent like convection oven baking. So there is also advantage of hot plate usage in the pre-bake. So a narrow time temperature window is needed to achieve proper line width control. So after after pre-bake, the thickness of the resist is usually decreased by 25% during pre-bake for the both positive and negative. So this is a temperature and dissolution rate. So you get different thickness when you go into higher temperature. So for use of convection oven, solvent at a surface of resist is evaporated first, which can cause a resist to develop impermeable skin, trapping the remaining solvent inside. Sometimes the bottom side is still soft because of the solvent is trapped in the photoresist. And heating must go slow to avoid solvent burst effect. So that's why it takes some time when you use oven. So the time is longer because it's a kind of slow process of baking. And conduction with a hot plate need an extremely smooth surface for good thermal contact and heating uniformity. So it's for the both side, the substrate might be very smooth, very flat, but somehow it always the surface of the hot plate which is not that smooth. So we have to make sure that surface of the hot plate or the contact between the substrate and the hot plate is good, so that every surface or every point will have a contact with the hot plate so that heat can be transferred accordingly. So temperature rise starts at the bottom of the wafer and works upward. So more thoroughly of evaporating the coating solvent. So it's a contact heating, so that of course we put the substrate bottom on the surface of the hot plate, then it heated from the bottom and go to the photoresist itself. And generally much faster and more suitable for automation. So as shown before, it's only for a few seconds, 45 seconds for example. So that is a faster process rather than 30 minutes or 20 minutes process for the pre-bake. And after pre-bake, then we expose the substrate or the materials with exposure of UV to the light. We have a chrome on glass photomask. This is the photomask. So this is where it's not covered. Then the light will pass through. The UV will be passed through here and expose this photoresist part to the light. So then it depends on what kind of photoresist you are using. So if it's negative, you can get this pattern. The exposed part will be the pattern. If it's a positive photoresist, the unexposed part will be the pattern, meaning to remove the exposed part. So this is, I mean, a repetition of what we have seen before. So now the contact aligner. So first, maybe it's not that critical to align the positioning, but if it's about second or third process for the development of the structure, so you have to be careful with the alignment. So the alignment with the photo mask and the structure that have been developed before will be critical in order for you to develop the next structure, because it has to be according to what have been developed on the surface. So the alignment need to be, this is, I mean, this is contact, which is the mask is in contact with the photoresist. This is aligner, which is just proximity. So it's not that, I mean, less wear on mask, but poorer image then form a contact aligner. So meaning to say, it's not in contact just above a few maybe nanometer or micrometer on top of this mask, on top of the photoresist. Then this is a projection aligner, which is I mean, you have a certain, this kind of setup projection system use imaging optics in between the mask and the wafer. So you have imaging optics here rather than just only here. So the lens is only here. So in this case, you have another optical setup in between the mask and also the substrate. So alignment and exposure. For simple contact, proximity and projection system, the mask is the same size and the scale as the printed wafer pattern. So the production is with the pattern is 1:1. So by design, you design a 50 micron line. So basically, you transfer the pattern of 50 micron on the substrate or the photoresist. And projection system give the ability to change the reproduction ratio. Going to 10:1 reduction allows larger size pattern on the mask, which is more robust to mask defect. So mask size can get unwieldy for large wafers. And most wafer contains an array of the same pattern. So only one cell of the array is needed on the mask. This system is called direct step on wafer or DSW. This machine also called steppers. So advantage of stepper is only one cell of wafer is needed. So the disadvantage is the one cell of the wafer on the mask must be perfect, absolutely no defect, since it gets used for all die. So higher end research system go one step further and use direct write on wafer exposure system. So this can be accomplished using laser, basically, with a geometry of 1 to 2 micrometer, and electron beams for geometries down to 0.1 to 0.2 micrometer, and focus ion beam for the geometries down to 0.05 to 0.1 micrometer. So in this case, no mask is needed for this technology. So you just expose the laser or the beams directly. It's a kind of write directly on the photoresist. These are serial processes, and wafer cycle time is proportional to the beam writing time. The smaller the spot, the longer it takes. So it depends on how big is your line. So if it's you are using 0.1 micrometer, I mean less 0.5 micrometer line, so you want to make a 50 micron, so that means you have to pass through so many times. So photomask, master pattern which are transferred to wafer. So that is what we have been calling as a photomask or mask. So the types of photomask: photographic emulsion on soda lime glass is the cheapest, or Fe2O3 on soda lime glass, or chromium on soda lime glass, or chromium on quartz glass. So these are types of photomask that can be used. So the dimension typically in research or in production, 4 inch by 4 inch with a thickness 0.006 inch for 3 inch wafer, and 5" times 5" of the same thickness, 0.06" for 4" wafer. So that is the photomask used. So mask aligner. So this is a kind of normal or common pattern for alignment. So we design this kind of thing as well on the photomask. So 3 degrees of freedom between mask and wafer, X, Y, and theta. So you want to align this kind of shape when you have your photomask with the kind of shape that the shape will be aligned very well, I mean, on this direction and this direction. So it will provide you with X, Y, and theta. So alignment mark on mask and wafer to register pattern prior to exposure. So if you have a few times of exposure and masking, this marking is critical. So modern process line use automatic pattern recognition and alignment system, and usually take 1 to 5 seconds to align and expose a modern stepper. But if it's a manual, sometimes it might take a lot of time for you to do the alignment. So human operators usually take 30 to 45 seconds with well-designed alignment marks. So it's quite difficult. So for example, this is, you have 2 camera here, and you have alignment mark at the end of this and at the end of this. So you make sure that if you align both perfectly, then you are at a good position where you have X, Y, and theta being aligned. So this will make sure that your next going to develop pattern will be accordingly transferred to the substrate. And you can have this kind of alignment as well. So this is typical aligner. So you have this kind of table, wafer stage. Then you have height adjustment. Then you have vacuum chuck. Then you put your wafer substrate on this. Then this is your mask, or the photo mask we call it. Then some, setup. Then you try to align this wafer stage accordingly for the X, Y, and Z. X, Y, and theta. So try to align so that this will be aligned for the whatever pattern that you have. So then once you have transfer the pattern on your photoresist, then you have you do post bake and to stabilize the photoresist to make it harder, so that you want to do the next process of developing the pattern on the substrate. So basically, you don't want to go too much on the post bake, because sometimes it will harden and it makes difficult for you to remove the photoresist. And post bake can happen in with a certain degree. Photoresist will undergo plastic flow with sufficient time and temperature. It can have this kind of issues as well in the post bake. Then this is when you have your pattern, you want to remove the photoresist, everything using solvent. Simple solvent are generally sufficient for non-post-bake photoresist. So you use positive photoresist, use acetone, TCE, and phenol-based strippers. And for negative photoresist, you use methyl ethyl ketone and methyl isobutyl ketone for the negative photoresist. So this will wash everything out of the, from the surface of the substrate. And in some cases, you might need plasma etching with oxygen. We call oxygen etching as well. It's also effective for removing organic polymer debris. Sometimes it's hard to remove something, then you can do plasma etching. And For microfabrication, photolithography is about process. If you want to add some structure or you want to remove some materials and you modify certain design, and it's about you deposit materials or you subtractive is about etching, and modifying is about doping, annealing, and curing. So that is about photolithography. And two primary techniques for patterning additive and subtractive process is etch back and lift off. So this is what is called as etch back. So you have a thin film deposit, then you have your photoresist, then you with this photoresist you remove this part of material, then you remain what intended for the process. This is what we call as etch back. And lift off, basically you have photoresist pattern on the substrate, then you deposit the thin film that you want to have. So basically all thin film covered the surface, including on the surface of the photoresist. Then you develop basically photoresist. When you put on the solvent, this part will be removed. The photoresist part will be removed, then you will remain the things up in the thin film which deposit on the substrate itself. So this is what we call as a lift off. And I think this is what we have. I have shown before. Maybe I don't need to explain it anymore. The photoresist photolithography process pattern transfer. Okay, I think that is about photoresist, and I would like to show a video as well on the short video to wrap up on the photolithography. Okay. All right. How is it? It's not working.
Cell phones, computers, televisions, and any high technology product requires the use of printed circuit boards, microcontrollers, or integrated circuits.
No. Some.
The components of these devices are extremely small. If they are too
How
small,
many minutes? Right? Is it too long?
These products are made using a technique called
How many minutes is it? Maybe RCP cleaning. I think. How many minutes? I'm afraid it's too long. Hmm? No time, right?
Cell phones, computers, televisions, and any high technology product requires the use of printed circuit boards, microcontrollers, or integrated circuits. How are they made? The components of these devices are extremely small. If they are too small to be seen by the naked eye, how is this possible? These products are made using a technique called photolithography. Photolithography is the process that transfers shape. Cell phones, computers, televisions, and any high technology product requires the use of printed circuit boards, microcontrollers, or integrated circuits. A layer of silicon is placed to resist consumption, 100 RPM, for 30 to 60 seconds. A mask that resembles the chip's geometry is held above the resist-coated wafer. UV light of extreme intensity is directed downward through the mask and onto the wafer. This causes a chemical change in the photoresist that is exposed to the light by the mask. Developer is then used to wash away certain areas of photoresist. Positive photoresist, the most common type, becomes soluble in the developer when exposed and is washed away. With negative photoresist, unexposed regions are soluble in the developer, and they are washed away. In the etching process, a chemical agent removes the uppermost layer of the substrate in the areas that are not protected by the photoresist. This reveals the silicon wafer to the unprotected areas. After a photoresist is no longer needed, it must be removed from the substrate. This usually requires a liquid resist stripper, which chemically alters the resist so that it no longer adheres to the substrate. Silicon dioxide is deposited onto all regions of the wafer to layer any parts of the wafer that may have been altered in the cleaning process. Silicon dioxide that layers on top of the photoresist is removed and the first layer of the chip geometry is completed. The process is repeated to obtain different geometries at as many necessary layers to complete the chip's circuit design. A chemical agent removes all silicon dioxide from the wafer, and silicon is the only element remaining on the wafer. How has photolithography improved from 1855 to the modern day? The smallest degree of detail, or resolution, that photolithography can be measured by is determined by two factors: the numerical aperture of the optical system and a light source. The numerical aperture can be approximated with the index of refraction and the max half angle of the collimated light as shown in the picture.
That's
The
all
index of
for
refraction can
the
be larger or smaller.
video. So it's just to get you that with some animation to know the process of photolithography and the lift off and the construction of the pattern on the substrate. Okay, with that, thank you. Yeah, any question from the floor? Yeah.
Hi, sir.
Yeah.
Sir, actually, this is for high resolution pattern. Na. This photo lithography is for high resolution pattern. Na. What are the main critical parameters for this high resolution? What are the critical parameters?
Yes. Photolithography is about transferring the light pattern onto a substrate.
Yeah.
So it's on the use of UV, and then what is critical is on the pattern transfer itself, which is the use of the photoresist. So how sensitive is the photoresist will determine the size of the pattern, and how fine is the line of the photomask itself will define the pattern as well. So if you want to have a very fine, I mean, nowadays you are talking about 2 nano or 3 nano, right? That might be a different approach of a process with laser, etc. So that's why on the use of writing using laser beam, for example, that is 0.005 micrometer of the beam spot. So, and the use of lens. The lens, you know that the transfer should use a lens, optical lens. So the lens needs to be very high, highly precise, and highly kind of the surface will need to be very fine. So that will determine the quality of your pattern transferred to the photoresist.
Okay, sir. And also any minimum feature size for this one? Minimalistic.
Yeah,
minimalistic.
I understand you. I'm not so sure nowadays because I'm not really following the recent progress of the photoresist. I'm so sorry. I have no knowledge.
Okay, okay.
Yeah.
And okay, thank you, sir. Thank you very much.
Sir, in the while in spin coating, you said na sir, those coating inside a corner of the plate there is a wavy. It may while doing photoresist photography, it may differ
Yes.
measurements
Yes.
while removing material.
Yeah.
Those two corner there wavy.
Yes. That's why the process, the spin coating parameters, the RPM, is important. Apart from that, you have to have a control process. That's why you have spin coating. Normally, we will put a cap, lid on top of that in order to prevent the environment influence when you do spin coating. The air, everything. So the use of different RPM. Okay, right? So these steps is quite important, but it's not necessarily will work all the time. But that's why some optimization need to be done for different types of photoresist and maybe different size of wafer. So you need to kind of test it first. Maybe you have the general process step like this, but now here you, because this time might be longer or this time might be longer accordingly to have a good surface thickness. Yeah. Okay, thank you very much.